Okay, geometry. We got more with logic to deal with here. We're still going to use our statements like we did in the last section where we had P as a statement that has a truth or false value, and Q is a statement that has a true or false value. But we're actually going to give names to our P and Q's name. They're not just going to be P and Q. They're going to be something a little bit different. We're going to have a name for them. That's what we're going to find out in this video. And we're going to look at what we call conditional statements. You've dealt with conditional statements all your life. If you clean your room, then you get to go do something. That's a conditional statement. It requires that the first part be done. And if you don't do that first part, and more than likely the second part won't happen, you see the meaning of that. So let's go ahead and get going here. We have these statements again in vocabulary that you're going to understand. Make sure you leave yourself some room there to work with each one of those, but those are the words you're going to want to use in your vocabulary. So now, our first one is the conditional statement. A conditional statement is any statement that can be made or written in the if-then form. So if I can get it into that if something then something, we're in great shape. So here I happen to have a card that says get $1,500 cash back when you buy a new car. Now if I can write that as an if-then statement, I have a conditional statement. Well, let's see. If you buy a car, then you get $1,500 cash back. That is an if-then statement. And that's the way that works, if we can put it in that. Now, what does that mean? Well, it means you have to buy a car before you can get $1,500 cash back. You don't get the money back unless you buy the car. So, if-then statements, if it's written in the form of P, then Q. So, it could be, we have an arrow here for our logic symbols, P arrow Q, and that is read as if P and Q, or you can say P implies Q. So if P is true, that implies that Q has to be true for the thing to work. Anyway, immediately following the if is a hypothesis. So this you buy a car is our hypothesis. And the phrase immediately following the word then is the conclusion. So you get $1,500 cash back is our conclusion. So if you want to find the hypothesis and the conclusion, I look at this. Now, what we find out is, as we work through these, trying to make these if-then statements. When I do that, when you want to write an if-then statement, you need to identify the condition that causes the result of the hypothesis. So what is causing the result? The result is the conclusion. So let's take a look at one. I guess I can delete this off of here. I have a statement here. And I want to identify the hypothesis and the conclusion, and then I want to turn the whole thing into an if-then statement. So here I have an angle with a measure greater than 90 degrees is obtuse. Well, what am I talking about? I'm talking about this angle with a measure greater than 90 degrees. So that would have to be my hypothesis, is that an angle has a measure greater than 90 degrees. Well, what's the result of that? The result is that I have an obtuse angle. So my conclusion is it is an obtuse angle. So how do I write that as an if-then statement? I say, if an angle has a measure greater than 90 degrees, then it is an obtuse angle. Okay, let's take a look at another example. Perpendicular lines intersect. Now what we're going to find out here, sometimes, like this statement, you have to add information to it so it makes sense. We know that for perpendicular lines, you have to have two of them. You have to have two lines that intersect. So what's happening is, here I have perpendicular. That's the cause. So that means I would say two lines are perpendicular. It takes two of them to be perpendicular. Well, what's the conclusion? Well, the conclusion is we got an intersection. So if these two lines are perpendicular, they're going to intersect. So now when I write my if-then statement, I'm going to say, if two lines are perpendicular, then they intersect. And that's how I write my if-then statements. Now, every one of these conditional statements, every one that we've had on the page, has a multitude of true and false values. So, if an angle measures greater than 90 degrees, that could be true or false, depending on the angle I have. Then it's an obtuse angle. Again, that could be true or false, depending on the angle I have. Okay, so let's take that one for instance. We're just gonna use that one. That'll get down to that. So if an angle has a measure of 90 greater than 90 degrees, then it's an obtuse angle. So let's say I have a measure of angle 1, and it happens to be 95 degrees. It is obtuse. With this one, it would seem to tell us that our conditional statement up here is true. Because I had an angle more than 90 degrees, and it was obtuse. Now, let's get another one here. I have the measure of angle 2. Measure of angle 2 is 215 degrees. It is reflexive. I spelled reflexive. There we go. IVE. So this would say the statement is false, because I found an angle that was greater than 90 degrees, but it is not obtuse. So every statement that we have can be true or false. So a common misconception is that a true hypothesis would mean that you have to have a true conditional. Well, this blue one shows that that's not true. I had a true hypothesis. I had a 215-degree angle. It was more than 90, but it wasn't. What's the word I'm looking for? Obtuse. Okay. Likewise, if I have a false conclusion, it does not guarantee that the conditional is also false. So what if I had? I don't know. This one's not going to work. But what if I had something that worked in those ranges? We'll look at that later. Okay. So a converse, an inverse, a contrapositive are other statements based on a given conditional statement, and they're known as the related conditions. So each one of these is its own special thing. So here we have our very first conditional statement. It's an if-then statement. So we are given a hypothesis and a conclusion. So we have our P implies Q logic. And our example for this one is if two angles have the same measure, then they are congruent. So that's our statement. Now when you read that, could that be a true statement? If two angles have the same measures, then they're congruent. Is that true? I would say yes. That is a true statement. So I would say this is true. If two measures have the same. Okay. Now, the converse. The converse, what I do is I change the hypothesis and the conclusion of the original conditional statement. So instead of saying P implies Q, I'm going to say Q implies P. So I'm swapping it around. So in our case here, if two angles are congruent, then they have the same measure. Again, that can be true or false. I would say it's probably true. If they're congruent, if they have the same measure, they're going to be congruent. I would say that's still true. Our next one is the inverse. The inverse comes about by negating both the hypothesis and the conclusion of the original if-then statement, of the original conditional. So what we're looking at here is our not P implies not Q. So if not P, then not Q. So if two angles do not have the same measure, then they are not congruent. That would be our statement there. Again, to me, that seems like a true statement. Now, we have what we call a contrapositive, negating both the hypothesis and the conclusion of the original statement and of the converse statement, negating both the hypothesis and the conclusion of the converse statement. Or you can think of, okay, I'm going to negate the hypothesis and conclusion of the original statement, and then I'm going to do the converse of it. So what I'm getting is, I'm getting a not Q, not P. So if two angles are not congruent, then they do not have the same truth value. This happens to be true too. In this case, if we get something along these lines where all of these are true statements, we typically refer to that as being a definition, and we can write it as an if and only if statement, but that's later on down the road. Now what happens is we get things that are considered logically equivalent. In other words, they end up with the same truth value coming out. So each of these happen to be all true, so we could say that all of these happen to be logically equivalent to each other. Now here's another possible example of a truth table for some P and Q conditional statements. And the original statement is if P implies Q, then it's true, and if it's, anyway, you got this table. Now notice our conditional and our contrapositive, the truth values for every single case are the same. We say they are logically equivalent. The original conditional and the contrapositive are logically equivalent. Now, in this particular case, the converse and the inverse also had identical truth tables. We considered them logically equivalent as well. So anytime the entire truth table for any conditional statement is looked at and they're identical all the way down, we call those logically equivalent. I think that's the only thing I got. Oh, there we go. Contrapositive. To write a contrapositive of a conditional, it is helpful to first write the converse of the condition. The relationship of the truth values of a conditional statement and its contrapositive is known as the law of contrapositive. So here's the thing. If I have a contrapositive, it will or should always be logically equivalent to the original conditional. The contrapositive and the original conditional will always be logically equivalent. They have to be. It's the idea behind that. And that's what this law of contrapositives means. It's the reason O.J. Simpson got off. The prosecution was saying he killed them, and these are the gloves he wore to do it. So if he killed them, then he wore gloves, and the gloves he wore were the ones they had in the room. Now, the prosecution went the other way. Well, if the gloves that are here in the room don't fit him, then he must not have killed him. They did the complete opposite of it, and that's how they got O.J. off. Now, here I have some example problems. You can find these in your textbooks on page 78 if you want to see them a little more clearly. So the first set of problems here, 4 through 6, we just need to identify the hypothesis and the conclusion of each statement. So I'm going to do that real quick. For number 4, the hypothesis is it rains on Monday. That's the hypothesis. It rains on Monday. Not the if, but just the it rains on Monday. That's the hypothesis. For number 5, the hypothesis is x minus 3 equals 7. That's the whole hypothesis, just the part after the if. For number 6, the hypothesis is a polygon has 6 sides. It's just the part after the if, all the way up to the comma. That's our hypothesis. Our conclusion is the part that comes after the then. So on our first statement, if it rains and I will stay home is my conclusion. For number 5, it says if x minus 3 equals 7, then x equals 10. Well, x equals 10 is my conclusion. For number 6, if a polygon has 6 sides, then it is a hexagon. Well, it is a hexagon is my conclusion. So that's how we do that. Now, I want to write, for 7, 8, and 9, write an if-then statement for each of these things. So I have a statement that says, for number 7, a 32-ounce pitcher holds a quart of water. So again, remember, what we want to do is figure out what is the hypothesis, what is the conclusion. Well, our hypothesis here is we have a 32-ounce pitcher. The conclusion is that it holds a quart of water. So how do I write that? Well, here's a possible way of writing it. If a pitcher is a 32-ounce pitcher, or if something is a 32-ounce pitcher, then it holds a quart of water. That's how I would do that one. Gonna get that in that way. Okay, let's look at number 8. The sum of the measures of supplementary angles is 180. This is a kind of a strange one because of the way it's written. The sum of the measures of supplementary angles. Supplementary angles is my hypothesis. The conclusion is that their sum is 180. Angling participle. There's the word I was looking for earlier. So I have to, this sum of measures goes with that 180. So that together is a conclusion. So when I go to write that one, I would say something along this lines. If 2 angles are supplementary, then the sum of their measures is 180. And that's the way I would kind of write that one out there for number 8. Okay, so now the next set, 10, 11, and 12, we have to determine the truth value of the conditional statement based off of the condition that is below. We don't care if this original statement is true or false, irrelevant. That is our statement. If you drive faster than 65 miles per hour on the interstate, then you will receive a speeding ticket. That's all we're looking at. So if number 10 says, well, if you're driving 70 miles an hour and you receive a speeding ticket, what does that tell us about this conditional statement? It tells us that conditional statement was true because the hypothesis was true and the conclusion was true, which meant it was a true statement. Now the second part, if you drive 62 miles an hour, then you do not receive a speeding ticket. Well, I did not get a speeding ticket, so this must be a true statement. Okay, now, number 12, you drive 68 miles an hour and you do not receive a speeding ticket. Well, that means our hypothesis was true that we were driving more than 65 miles an hour, but we got a false here on the conclusion. That's a false statement. Anytime the conclusion is true and the hypothesis is false, you have a false statement. Anytime that your hypothesis is false, it depends on your conclusion on whether or not it's true or false. If your conclusion is true, then your statement can be true. Now, the last set here is we have to be able to write the converse, the inverse, and the contrapositive of any statement. And we're just going to look at the number 13 there. So let's ignore this one here. Number 13. If plants have water, then they will grow. So our converse of that is to flip the hypothesis and the conclusion. So if plants grow, then they have water. That would be our converse. All I did was switch the grow and they have water. Now the inverse says to negate both the original conditional statements, hypothesis and conclusion. So if plants, if plants don't have water, so the original plant says plants do have water, so now I say don't have water. Well, then the opposite of they will grow is that they will not grow. That would be its inverse. Now the contrapositive is combining these two, or thinking, okay, I'm going to take that inverse and I'm going to do the converse of it. I'm going to flip it around. So what I'm going to say is if plants don't have water, then they don't grow. Now let's see how this works out into our statements. If plants have water, then they will grow. Is that a true or false statement? Well, in most cases, we could say, well, that's either true or false. True because, yes, they need water to grow. False, well, they also need light. That would have to work. So because they might also need light, that would say it's false. If they don't have light, they may not grow. So we'll call that false. If plants grow, then they have water. Well, that's a true statement. If they're growing, they have to have water. That's one of those nourishment items that they have. They have to have water and they have to have light. Now, the inverse, if plants don't have water, then they don't grow. Well, that's true also. If they don't have water, then the seed will never break down, the plant will never grow. That's a true statement. The contrapositive, if plants don't have water, then they don't grow. Well, that is a false statement. Because plants could have water and not grow. Think of a flood. If I have a flood, I've got all that extra water and the plant won't grow. So that is also a false statement. Now, once again, notice our contrapositive and our original statement happen to have the same truth value in them. And it worked out here again that our converse and our inverse happen to have the same truth value. So they're logically equivalent. So now what should you be able to do? You should be able to do assignment number 26 on page 78, 16 to 38 even. You're just doing this kind of stuff. Get going.